Um, well, first of all, thanks, Philip, for the very nice introductory talk and to the session. And I also would like to thank the organizers of this conference for the invitation. I'm really sorry I couldn't be there in person. I really was looking forward to visiting your institution and also your country. It would have been my first time, actually, but I have a newborn at home, so I'm kind of grounded for a little while. And so if you hear some crying in the background, you also know what's going on. But nonetheless, thanks for arranging this in a hybrid mode. It's still great to have a chance to talk to you and to your audience about our work exploring the electronic band structure of this family of materials, which really has gained a lot of traction and drawn a lot of attention in the past few years, these Kagome metals, which have emerged as a new platform for studies of quantum matter phenomena in condensed matter systems. And I will kind of take you through different examples today. This is the outline of my talk. I will start with an introduction on the kind of quantum matter phenomena that can be potentially hosted or engineered in the Kagome lattice. And then I will discuss two examples from our work of the past 4 or 5 years. One of them is about the study of electronic topology, and in particular, topological bands in some simple binary Kagome metals from the family of the transition metal stanides. And I will tell you about topological Dirac fermions and associated transport signatures of that buried curvature, as well as topological flat bands in the same family of materials. And then in the second part of my talk, I will switch gears a little bit and discuss a different class of phenomena, in particular electronic symmetry breaking in a different family of Kagome metals, which also happen to be Kagome superconductors. And I will try to connect that to other features of the electronic band structure, specifically the presence of van Hove singularities. So let me first acknowledge the people who actually did the work and deserve the credit, and in particular for this first part, which is about the study of electronic topology in Kagome systems. The two people who really deserve all the accolades for everything that came out of this work are these two young students, Mingo Kang from my group and Linda Ye from the group of Joe Chekelski. This was started as a collaboration between Joe's group and mine. In fact, the very first results that sort of got us motivated to look at these Kagome metals from the perspective of the electronic band structure were some interesting magnetotransport data coming out of Joe's lab. And then this has become really, a major research direction for both our groups. And this has been really masterfully carried forward by these two fellows. So, and Mingo Kang is a graduate of Postec, and then he came to MIT for his PhD, and so he's been doing really outstanding work. And basically, almost all of the data, the experimental data that I will show you today, that were taken using angle resolved photo emission as a probe of the band structure, they were all taken by Mingo. So really, he's done really remarkable work on this. And then this work has been done at external facilities. This is our synchrotron ARPES, which is the best tool to explore the electronic band structure of new materials, really. And it's relied on a lot of support from the theory, in particular from the groups of Tim Kaxiras and Liang Fu across Harvard and MIT, and also from the group of Jeroen van den Brink at IFW Dresden. All right, so let me talk about quantum matter phenomena and the Kagome lattice. So first of all, why, what kind of phenomena are we talking about in this case? So to stay, sort of in tune with the topic of the conference, I fine-tuned this talk to focus on the phenomena that can happen or can be realized at the confluence of electronic correlations and electronic topologies. So on one hand, we have many body effects that arise and emerge in systems that have strong electron-electron interactions, which leads to correlations between the behavior of different particles or different electrons. And on the other hand, we have a different manifestation of the quantum mechanical properties of the of electrons in solid, which is the creation of some effective emergent electromagnetic effects due to the presence of Berry curvature and Berry connection, which is reflected in the non-trivial topology of the single particle bands. And so on this side, we have various examples of exotic physics that we're interested to study in the context of quantum materials, and this includes multi-insulating physics, superconductivity, charge density waves, and pair density waves. These are all forms of different many-body states which have wildly different properties, and in many cases need to be described by sort of quantum mechanical wave functions that involve many electron states. So these are really coming in the form of condensates. And on this end of the spectrum, we have topological phenomena, which includes quantum spin Hall, 3D topological insulators, bi-semimetals, nodal line semimetals, and many other examples. So when we look at what happens when we have systems that exhibit both strong correlations and non-trivial topology, we find actually many examples of very interesting physics, some of which you have heard in the talk from Philip. So churn and action insulators, magnetic vial, fermions, fractional quantum Hall effect, topological order, Majorana fermions, and so on. So what I'd like to kind of convince you of today is that the Kagome network as a building block of some solid systems, some solid state systems, can actually be an ideal platform to realize some of these phenomena. And I will focus mostly on the demonstration that the Kagome systems harbors the electronic band structure, which is conducive to supporting this phenomenon. And I will also give you some example of these phenomena and how they manifest themselves. In particular, I will show you examples of electronic topology and how it connects to transport signatures, as well as examples of electronic symmetry breaking and how it potentially arises from the features of the electronic band structure. So this is the Kagome network. So the atoms are located, the atoms are these small circles here. They occupy these sites on a unit cell which contains 3 sublattices, so A, B, and C. So this is one sublattice in addition to the honeycomb system or graphene. But the Kagome shares a lot of common traits with both the triangular and the honeycomb lattice. In fact, it has the very same point group symmetries. And the only difference between these 3 lattices is the number of atoms in the basis set of the unit cell. So the triangular lattice only has 1 sublattice, the honeycomb has A and B, and Kagome has A, B, and C. So in a way, we can think of the Kagome lattice as a system which can realize some of the physics of honeycomb systems like graphene, but potentially even richer because it can host multiple bands in addition to the ones of graphene. And so this is very powerfully shown by even a simple tight binding calculation of what the bands of the Kagome lattice look like. And if you neglect this flat band at the top, which is important, and I'll come back to that in a second, if you look at the rest, you have these 2 bands which are the same that you would find in graphene under the same conditions for the calculation. So assuming only nearest neighbor hopping. And so you have the Dirac fermions at the K point, you have the Van Hove singularities at the M point, so you have vanishing density of state at the Dirac point, and then an enhanced density of states at the Van Hove singularity because you have this saddle point dispersion where there is a pileup of density of states. And in addition to the bands that are known from other systems like graphene, you also have this flat band, which arises because of the very peculiar hopping pathways that exist on the Kagome lattice. And I will not discuss that in detail, but it's a really beautiful phenomenon that is peculiar to the Kagome lattice and occurs because there is essentially a mechanism of destructive interference in the hopping pathways that involve electrons that are trying to delocalize themselves in the solid, in the lattice. All right, so these are the main features of the band structure of the Kagome lattice, and I'll come back to each of these throughout my talk. So I will start with a discussion of what happens when you have, Dirac fermions and spin-orbit coupling, and how the Kagome lattice can be effectively an embodiment of the K-Melee model in that limit. And then I'll discuss an example of flat bands in the same family of materials and how also those can be endowed with non-trivial topology. And then in the last part of my talk, I will focus on the role of Van Hove singularities in electronic symmetry breaking. So indeed, if we look at the different features of the Kagome lattice, as I was just saying, you can have localized sources of Berry curvature at all points where you have degeneracy. So that would be the K point and the degeneracy between the 2 Dirac bands, and the gamma points where you have a quadratic band touching point between the Dirac bands and the flat band. And so if you have spin-orbit coupling would open a gap, and that gap would give you a local source of Berry curvature, and that's in the limit where you're looking at a k-point fermions. That is essentially the Kane-Melle model, and that is realized actually in many of these Kagome systems, including magnetic ones. So you see here a list of them. If you now kind of play with the chemical potential and shift it close to the Van Hove singularities, now you're or the flat band, now you're in a different limit where the phenomena you can realize are enabled by having a large density of states at the Fermi energy, and the system typically doesn't like that. So it wants to remove that degeneracy by breaking symmetries. And so if you can come up with materials that whose chemical potential or Fermi energy is tuned or located close to the Van Hove singularities or the flat bands, you can actually realize a whole realm of different physics, which includes a lot of strong correlation phenomena that come in the form of symmetry breaking. So things such as charge order, superconductivity, pair density waves, and so on. And all of these phenomena have been discovered in this second class of Kagome materials that I will tell you. Okay, so why we're interested in studying these? Because they can be a possible platform for even more exotic forms of quantum matter, including the fractional quantum Hall states, which have been predicted to happen up to potentially high temperatures in the Kagome network. And this is like a seminal paper that motivated a lot of people to look into this particular phenomena and this particular lattice. And this was from my colleague Xiaogang Wang. So we're kind of following in the footsteps of the theory in a way in these explorations. And the first family of materials that we looked at is the family of transition metal stanites. And these materials come in different shapes and forms, and they have a fairly versatile stoichiometry where you can change the ratio between the transition metal and the metal, so the transition metal can be anything like iron, manganese, cobalt, and the metal can be germanium, tin, indium. So there's quite some variety, both chemically and structurally. And what you can do structurally is by changing the stoichiometry or the ratio between the number of Kagome layers to the number of stannine layers, which are interleaved between the Kagome layers, you can actually tune the dimensionality of these Kagome systems from being more three-dimensionals, or the limit where you have strong inter-Kagome layer coupling. So, and this is the limit where you only have Kagome layers which are facing each other. So you have Kagome, 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 and just basically a repetition of Kagome layers. To the two-dimensional limit where you have the Kagome layers being isolated and separated out by a layer of stannine. And clearly the layer of stannine is not insulating, so it's not like an insulating barrier, but still it acts to reduce the interlayer coupling. And we see this kind of effect in the electronic band structure. And then you can construct systems which are intermediate between these two. These are some of the examples of the beautiful crystals that are grown in Joe's lab and that we have had the fortune to study in this past few years. And one particular aspect that is specific to this class of materials, this transition metal stanites, which sets them apart from a lot of other systems where people have been looking for interesting topological effects, is that many of these materials are magnets. And many of these are room temperature magnets. Like iron 3 tin 2, which is the first material that I will tell you about, is a collinear out-of-plane ferromagnet with a Curie temperature which is above room temperature. They have spin-orbit coupling from 3D orbitals, which is not gigantic, but is in the order of a few tens of milli-electron volts in some cases. And we do see the signatures of this spin-orbit coupling very clearly, both in transport and in the spectroscopy, in the photo emission measurements. And of course, because we have 3D electrons, which are more localized than the P electrons, then we have intermediate Coulomb interactions. So potentially a place to look for correlated physics that's activated by the presence of DD Coulomb interactions. Okay, so let me tell you first about the topological Dirac fermions and flat bands in some of these transition metal stanites. And this all started with some interesting magnetotransport data from Joe's group that date back to, I think, 2017. So this was 6 months after I joined MIT and was in the process of setting up my lab. And then we were having a discussion with Joe about these interesting anomalous Hall transport data, where, to make a long story short, what they were seeing that the strong temperature dependence of the anomalous Hall conductivity could not be fully explained just simply with extrinsic effects. So the extrinsic effect is the one that the extrinsic contribution to the anomalous Hall conductivity is the one that scales with the conductivity, with the longitudinal conductivity, and therefore it increases as you lower the temperature because the conductivity goes up, the longitudinal conductivity. But then in addition to this contribution, which kind of vanishes at high temperatures anyway, there is another contribution which is almost temperature independent and cannot be really explained with a scaling of the longitudinal conductivity. And so this contribution must be intrinsic. And it's temperature dependent, which suggests that's potentially a manifestation of band topology. So something which is completely intrinsic to the electronic band structure that underlies the transport measurements, the macroscopic transport measurements. This system is also a magnet, mind you. So this is why you see the anomalous Hall transport, and this is key to what I'm going to tell you about. So this is a system that breaks time reversal symmetry, has predominantly out of plane magnetization. So we looked at these systems using angle result for emission spectroscopy, which I will not discuss in detail. I know many of you are familiar with the technique. It's a fancy version of the photoelectric effect that was discussed by Einstein. Essentially, we shine ultraviolet photons onto our sample. We can photo-eject electrons right from the surface because of the short mean free path of electrons in matter. And then we can analyze the energy and the takeoff angle of those electrons. And from those, simply by applying conservation laws, we can reconstruct the energy and momentum dispersion of the electronic bands inside the solid. And so you can generate these beautiful maps. This actually came out from the very first experiment we did on these samples. This was led 100% by Mingu, where we looked at the dispersion of the electronic bands across the K point. And so if this system was like, say, was similar or equivalent to graphene in the vicinity of the K point, what you would expect is a single Dirac fermion. A pair of Dirac fermions meeting at a Dirac point, which is right at the K point. So in other words, you would expect a single Dirac cone. And you do see a Dirac cone, which has a binding energy of about something like 60 milli-electron volts up here. But then there is a second Dirac cone. So there is a second pair of Dirac bands that has a Dirac point, which is at deeper binding energy, a larger binding energies. And so this is happening because of some hybridization between the Kagome bilayers, in particular between the Kagome bilayers. They face each other, so they hybridize and they form something that you can think of essentially as a bonding anti-bonding splitting. So one of these bands is the bonding band, the other one is the anti-bonding band. It's very simple hybridization physics. But the interesting thing is that if we take this dispersion and we analyze it, and we look at the spin-orbit gap that exists at the K point and which is of order of 30 milli-electron volts, which we can obtain from the ARPAS dispersions, which are shown here in the data points. So if you do a KP modeling of this band structure and you calculate the resulting sigma xy, or the resulting anomalous Hall conductivity, by assuming the Fermi energy is in the place where it is experimentally, then you get a value which is within something like 10%, 10-15% of the value that was observed by transport. So this suggested that there was a strong connection between the electronic band structure and the transport data, which we could validate quantitatively by looking at the dispersion of these massive Dirac fermions in the system. And so this is all nice and interesting because it provides a first manifestation of topology in the Kagome systems, and was the very first discovery of the presence of massive Dirac bands in a Kagome material. So it kind of like opened the gates for a series of other studies which we performed in the years to follow. And one thing that we were particularly adamant to find was the flat bands. And we wanted to find the flat bands because we wanted to provide experimental proof that they exist in these systems, in the band structure of these materials. And the reason for doing that is because there is a lot of interest in using the flat bands as a starting point to achieve some correlation phenomena, sort of like of the same kind as the ones that can be realized, that can be achieved in magic angle twisted bilayer graphene, where the flat bands are created by the Moiré engineer. So one approach to this that we followed together with Joe, was to try and look at a simpler system with more isolated Kagome layers and with cobalt instead of iron, because cobalt has extra electrons. And so if we look at the chemical potential in iron 3 it lies over here. So it's below the flat band. So we cannot see it with photo emission, which only looks at the bands below the Fermi energy. So what we did was we artificially raised the chemical potential with respect to these bands by substituting iron with an element which has an extra electron. So essentially, if you like, we're playing with electron filling, and we're raising the chemical potential that way. And so lo and behold, what we saw was this beautiful flat bands in cobalt tin, which is, it's really flat in all directions in momentum space. It acquires a little bit of a dispersion along the gamma to k direction, and that's due predominantly to next nearest neighbor hopping, which makes the bands not perfectly flat anymore, but it gives them a little bit of a bandwidth. But compared to the dispersion of the Dirac bands, which is of order 2 electron volts, these bands are really flat, and they are meeting the Dirac bands exactly where they're supposed to at the gamma point. So these are the flat bands that are associated to the same set of bands that arise from the same orbitals that give us the Dirac bands. And we find them at a binding energy of about 270 milli-electron volts, so not terribly far away from the Fermi energy, possibly within range of doping by gating if the Kagome layer could, if a single Kagome layer could be isolated and you could construct very similar devices, field effect devices that you can do with graphene. And it acquires this small dispersion only near the K point, again, due to the longer range hopping. And so if you look as a function of kz, so out of plane momentum, the band stays flat. So it's really flat along all directions. It's really, nice and beautiful and perfectly matching the DFT, kind of like a rare case in materials that are based on transition metals, but here it works really well. And most importantly, what happens is that at the gamma point, there is a gap that opens up that has a magnitude which we really didn't expect. So we observed a spin orbit gap, which is as large as 80 milli-electron volts between the flat band and the underlying Dirac band that reaches the gamma point and forms its quadratic band touching point. And so this gap arises from spin orbit coupling. It is predicted by DFT to happen at the gamma point. We have really no good idea or good understanding of why it is so large, considering that the atomic spin orbit coupling of cobalt is not nearly as large as 80 milli-electron volts. But experimentally and theoretically from band structure modeling, we find that this gap exists and endows the flat band with topology. So it's not a finite Chern number like in the case of the previous material, which has time reversal symmetry broken. But we still have a non-zero Z2 index, which we can find from analyzing the parity eigenvalues for the time reversal. For the time reversal symmetry preserving momenta. So the M points and the gamma point. And so the flat band is also topologically non-trivial, which is exactly the kind of situation that one hopes to have if one wants to realize phases that bring together topology and correlation, because really the common ingredient in the band structure of the Kagome systems that has both non-trivial topology and the ability to activate correlation effects is the flat band. Is the flat band because the flat band can be topological, as is shown here, once it's gapped out from the Dirac bands, and the flat bands has a divergent density of states, or at least a very large density of states. And so being able to sort of bring the Fermi energy to the flat band, also in the presence of topology, is exactly the place where one wants to be to realize all of these interesting phenomena that were predicted by Xiaogang Wang more than 10 years ago. So for the last part of my talk, I'd like to kind of talk about a different class of materials with same building blocks, so the 2D Kagome lattice, but with very different set of phenomena that mainly involve electronic symmetry breaking. Can I just check how much time do I have left? Is it 10 minutes? Okay, I think I have about 10 minutes. Okay. Right. So this work was, again, on the experimental side, carried out by Mingu. He did all the photo emission measurements. And this wouldn't have been possible if it wasn't for the outstanding work of Shang Fang, who was a postdoc at Rutgers at the time, and now he's at MIT working with Joe. And he did all the band structure theory, all the DFT and tight binding modeling, which was really instrumental to understand what was going on in the band structure of these materials. And we also had a collaboration with Giorgio San Giovanni and Domenico Di Sante at University of Würzburg and the Flatiron Institute, with Tim Kaxiras at Harvard. And most importantly of all, I want to really acknowledge the group of Stephen Wilson and Brandon Ortiz at the University of California, Santa Barbara, for giving us some of these samples that were really interesting for us to study in this project. And of course, I should actually mention also collaborators from South Korea. So big part of the work on the experimental side involved many people from the group of Jae-Hoon Park at Postec as well. So, and all the experiments were performed again at the Advanced Light Source in Berkeley. So this is this different family of Kagome materials. These are ternary Kagome metals. So the stoichiometry is AV3 SB5. So these are vanadium antimonides, and the first element is an alkali. So it can be potassium, rubidium, or cesium. This is the side view of the structure. So you have this kind of sort of a tetrahedral cage of alkali metals, and within this cage there are these Kagome planes, where the vanadium atoms are the ones that form the Kagome sublattice here, and the antimony atoms are sort of part of the antimonies are in the planes, and part of the antimonies are coordinated out of the planes. So it has this a bit peculiar stoichiometry 135, but the important thing is that structurally speaking, this is a layered system. And the fundamental unit of this layer system is the 2D Kagome network, and the atoms that are occupying the Kagome sites are the vanadium atoms, which is important because the system has a lot of multi-orbital physics that has to do with the different 3D orbitals that are brought in by the vanadium atoms. So this caught a lot of attention and really a big spotlight starting a few years ago. Thanks to the discovery of superconductivity and charge density waves in the very same materials. And, I did a lot of work on the cuprates. So when I hear superconductivity and charge density waves and phase competition, I, get very excited. And so it appeared from the beginning that this family of materials could be a new platform to explore different forms of electronic symmetry breaking and the competition between them. So superconductivity is happening at low temperature in these materials, is sort of temperatures that vary between 1.5 and 4 Kelvin, whereas charge density waves or charge order has an onset which is between 70 Kelvin and 94, 95 Kelvin, depending on the alkali metal. And so what happens at the symmetry breaking transition that gives us charge order? Well, what happens is that the pristine unit cell doubles in both planar directions. So you go from a pristine unit cell, which has just the ABC sublattice of the Kagome network that I told you about before, to a 2x2 enlarged unit cell, which can have different patterns, and that's still a matter of active debate. The example that you see here is the one called inverse Star of David, which essentially means that these hexagons shrink a little bit in the middle, and these triangles shrink also. And this gives you this overall distortion that you see pictured here. And so the characteristic wave vector, because it's a 2x2 distortion, is 1/2 0. So the characteristic wave vector that, of course, that gives you this distortion is a wave vector 1/2 0. So this is a period 2 charge order. So again, making a long story short, I don't really have time to give you the full summary about these materials. I think there are some few hundreds of papers that came out in the last couple of years. There's been a flurry of experimental and theoretical activity of research on these systems. So the various forms of symmetry breaking that occur in these systems are a cascade of different transition that starts with charge order at 94 Kelvin. Then you have loop current order, which has been detected with muon spin rotation that happens between 94 and 70 Kelvin. Uniaxial stripe order, so breaking of rotational symmetry as well, happening around 60 Kelvin. This is particularly from NMR measurements. And then a form of electronic nematicity, which was seen with STM and NMR that occurs at around 35 Kelvin, and then at last superconductivity and potentially pair density waves at very low temperature in 2.5 Kelvin. And so this is interesting because it puts these systems in sort of like a playground of other interesting platforms for quantum matter that we're all very familiar with. So the cuprates, iron-based superconductors, twisted magic angle twisted bilayer graphene, and so what we can see in this Kagome metals is that we have a competition between the charge density wave and superconductivity, which was proven with the pressure studies, where you can actually enhance the superconductivity and you have multiple domes of superconductivity concurrently with the suppression of the charge density wave. So there's a lot of physics involving symmetry breaking and competition between different phases. So the question that we asked ourselves is, what's the role of the electronic band structure in the formation of the charge density wave state? So if we now kind of look at, focus on a different part of the electronic band structure, which is specifically the Van Hove singularities, what happens if you tune your Fermi energy to one of the two Van Hove singularities in the band structure of the 2D Kagome lattice, what you see is that the Fermi surface is perfectly nested in the limit of nearest neighbor hopping only. So the Fermi surface looks like a perfect hexagon, which means that the flat portions of the Fermi surface that are facing each other are perfectly nested. And most importantly, the vector that nests these flat portions of the Fermi surface at the filling corresponding to the Van Hove singularity is exactly equal to the nesting wave vector. So it's exactly equal to this wave vector 1/2 0. And so at these Van Hove singularity fillings, what we have is we have a diverging density of states. That's a good starting point to have symmetry breaking. And then we have a perfectly nested Fermi surface as well. So there can be an additional reason for the system to want to order at a specific wave vector, which is the one corresponding to the nesting conditions. So this is the expectation, from the tight binding for the band structure of these systems. And this is the reality, which is very different, of course, and much more complicated. So you see a jungle of electronic bands here, but I really want to call your attention to this group of 3 bands, which are highlighted in red, blue, and pink over here. And the really remarkable thing that characterizes these materials is that it has multiple Kagome bands that arise from the fact that we have multiple 3D orbitals from vanadium, and each of those orbitals has its own set of Kagome bands. And they all have a Van Hove singularity near the Fermi energy, which really tells us that there's something special happening here, where these ideal conditions for symmetry breaking are potentially realized in this system. And so we see these 3 main Kagome bands are one that we call the K1 band, which is the pink one, which has in-plane orbital characters, so dxy, dx square minus y square orbitals, real space orbitals. The K2 band, which has out-of-plane orbital characters, so dxz, dyz, and which is the blue one, and the K2 prime band, which also has out-of-plane character, which has so dxz, dyz, and has the opposite type of Van Hove singularity. So the settle point is the same for the blue and the pink band. As you can see here, the dispersion is basically the same. They come up from the K point, flatten out at M, and then continue towards gamma, whereas the red band comes up from the gamma point, flattens out locally at the M point, not much in the case of this red band, and then continues towards the Dirac point, which is over here, and then towards gamma. So we can see these very clearly with photo emission. So what we expect when we look at band structure data are these dispersions where we have essentially a band that has a bottom. In the case of the p-type Van Hove singularity, we have a band that has a bottom and then a Dirac point at K, and the bottom of that band disperses upwards towards M. And the M point, you have the settle point, and then the band continues down. And this is exactly what we see for the K2 and the K1 band. So 2 of these Kagome bands, the pink and the blue that I was showing you just in the previous schematic, what we see is that they have this Dirac point that's below the Fermi energy, and then the bottom of these bands, as we move from K to M, so we crawl along the edge of the Brillouin zone, we see that the bottom of this Kagome band goes up, 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 and then reaches a maximum at the Van Hove singularity point, and then goes back down. And we see exactly the same behavior for both these bands. If we look at the other band, the K2 prime, which has the opposite type of Van Hove singularity, then we expect the same saddle point dispersion, just rotated by 90 degrees. So now we have a maximum coming back down from the K point, and then a minimum in this dispersion at M, and then the maximum of this sort of like hole-like band that disperses back up towards the K point. And that's exactly what we see. So we have this band that has a maximum at K, and that maximum disperses downwards, and then it goes back up. So the signatures are very clear. And when we look at the Fermi surface, remarkably, we have that the Fermi surface, presents the conditions for nesting for all these three bands. And we see this experimentally also very clearly if we look at the Fermi surface. We see these bands that have this Fermi surface, which has this hexagonal shape. And this hexagon is a little bit warped for this K2 band, this blue band. And instead, it's a much straighter hexagon for this K2 prime band. So potentially this K2 prime band is actually one that has good conditions for nesting. I'm gonna go a little bit quicker now and summarize in a couple of minutes so we have time for questions. So for these K2 prime bands, we do see a gap that opens up at the Fermi energy, like a charge density wave gap. But this gap is not too big. It's of order 20 millielectron volts, which could make sense potentially. But the real large gap that we see in the experimental dispersion is the one that involves the K1 band, which is a different band that also has a Van Hove singularity very close to the M point. You see it right here, where the dispersion becomes locally flat of this band, going from K to M back to K. And then as we enter the charge density wave phase, and we go all the way to low temperature at 6 Kelvin, we see a massive renormalization of the dispersion of this band by as much as 80 millielectron volts, which means that essentially the Chu delta over KBT is of order 10. So, potentially we're looking at something which is very strong coupling. So long story short, we try to disentangle the effect from the nesting from the effect due to the strong electron phonon coupling. And the conclusion is that nesting is not very strong because despite the fact that this Fermi surface looks very flat, looks like a perfect hexagon, it actually has a lot of KZ dispersion, and so it becomes very warped. And so the susceptibility is not really diverging at the endpoint. So the nesting conditions are not very good. But if we instead simulate what the band structure does when we distort the lattice, then the renormalization to the electronic bands is massive, which suggests that there is really a very large electron lattice coupling that drives the formation of the charge density wave. Okay, so with that, I basically am at the conclusion. So I just want to give a brief outlook and just flesh out the fact that we've had, a lot of exciting physics coming from, the field of graphene and twisted bilayer graphene in these last few years. And I just want to make the point that the 2D Kagome network, and in particular, a single 2D Kagome sheet, like something like a Kagome, could be potentially a new platform to realize the very same phenomena, but in systems that can support interaction energy scales and spin orbit coupling energy scales, which can enable these phenomena to happen at temperatures which are much greater than what can be realized in a twisted bilayer graphene. So with that, that's all I have, and thank you very much for listening to my talk. And I'll be happy to take questions.
Thank you very much. Now the talk is open for questions. Oh, yes.
So you showed churn, gap Dirac band formation and the Z2 gap opening in the two materials. So this signature has been also seen in transport, I guess. But is there an indication in the edge state?
Yes, great question. So, right. So in principle, if we could look at a single magnetic domains in this iron 3 tin 2, then we would expect to have a helical edge state around it. This is a weak this is a weak 3D TI system essentially. So each Kagome layer is in the quantum anomalous Hall limit effectively. And so yes, so one would expect, what in principle expect the signature of these helical edge state, but it has not been observed in this particular material, and it would probably require some probe with high spatial resolution, because this material has a very complex domain structure, and so one really has to look at edge states at the boundary of domains in the system. Yeah.
Okay. Yeah, thank you very much.
Yeah, but so in principle, so the other comment to that is that, strictly speaking, one would expect kind of like an edge state, of course, in the limit where the chemical potential is in the gap. In this case, the chemical potential is not in the gap, so the chemical potential is over here. So we do have anomalous Hall signatures of the Berry curvature in this system. So we have transfer signatures that there is topology. There is non-trivial topology in this material combined with time reversal symmetry breaking, so Berry curvature, that gives an anomalous Hall conductivity. But the Fermi energy is not in the gap, in the topological gap of the massive Dirac bands. So the Fermi energy is above here. And if it was in the gap of one of these two bands, and if we didn't have the other band, then strictly speaking, we would be in the quantum anomalous Hall limit, and then we would expect macroscopically an edge mode, and we would expect to see the signatures of the quantum anomalous Hall state. Yeah.
Thank you for a very nice talk. And I have a very simple question. Can you cleave a single layer from iron tin or cobalt tin? And if it is possible, do you have any expectation about the fate of a flat band? Would it be more flat, or it can be more dispersive?
Yeah, great question. So we tried, but we're good at cleaving crystals to get atomically flat surfaces, but we don't really have the best expertise or technology, at least across my group and Joe's group, to kind of really isolate or try to really do a exfoliation of single layers. So we tried our best, but we couldn't really thin these samples down to, in terms of thickness, less than a few hundred nanometers. The same is true also for these other family of Kagome superconductors, this 135 family, where other groups have succeeded to thin these down and isolate flakes down to, I believe, 10 nanometers or so, but no less than that. So these are not strictly speaking van der Waals. They have stronger bonding between the layers than van der Waals materials. They still have a layer structure, which is what enables us to isolate single and atomically flat surfaces for our photo emission measurements. But individual layers are not as easy to isolate as in other systems. But we're very much trying, and we're looking for other possible candidate materials that host the Kagome lattice and that have weaker interactions between the planes that could enable isolating a single Kagome layer. As far as your question about dispersions, I would expect that the dispersion in the single Kagome layer would look even more like the expectation from tight binding. So that would look even more like this set of bands here. At that point in the limit for a single Kagome layer, you would have no out-of-plane dispersion anymore. So if there is any hopping or any hopping amplitude between orbitals sitting across neighboring Kagome planes in the 3D system, which there always is. So there's always is a little bit of KZ dispersion, even though in many of these layer systems it's not very big. We expect that in the 2D limit that would go away. It wouldn't be there anymore. So in that case, we would expect the bands to be flat. We would expect to see just a pure single set of bands from the Kagome lattice, and that would really be the ideal limit to work in to realize the same kind of physics you can have in graphene with the addition of the flat band, of the intrinsic flat band in the Kagome layer.
Thank you.
Hi, thank you for your interesting talk. I was just interested about the outlook, where you said that the Kagome lattices can potentially have higher critical temperature compared to the twisted graphene. So maybe I didn't catch it, but why is that so?
No, it's not so much the lattice in itself, is the fact that we can, we have a variety of material system that host the Kagome lattice, and where the Kagome sites are occupied by transition metals, which have, Coulomb interaction energy scales and spin orbit coupling energy scales, which are greater than the ones that you can get in carbon-based systems. And so intrinsically, the energy scales for the interactions, whether it's Coulomb interaction or spin orbit, is greater in systems that that have transition metals, just because of the intrinsic properties of the 3D electrons. And this is sort of nicely confirmed in these Kagome materials, in particular in these transition metal stanites, from the fact that they can support magnetism up to room temperature and above.
Okay,
and we see
thank you.
spin orbit coupling. Yeah, and we see spin orbit coupling that varies between 30 and 80 milli-electron volts. It's really significant. It's of order KT or greater. So
Thank you.
it's pretty large energy scales at play in these systems.
Okay, yeah. Thank you very much. Yeah, let's end this first morning session. Yeah, thank you very much. Yeah.
Thank you.